Good evening, guys. This is the second in a two-part video series on Lewis dot structures, and in this one we're going to be talking about covalent Lewis dot structures. If you need to go and review on ionic Lewis dot structures, that would be in topic 5a. So let's get started with some rules. The rules for covalent bonds are a little bit different than ionic. So first, the difference between the bonds. Covalent bonds form between two nonmetals, and instead of an ionic bond where there's give and take of electrons, covalent bonds are like good little kindergartners, and they're going to share their valence electrons to try and achieve their noble gas state. So there isn't anything with a positive or a negative charge, because everything's just sharing their electrons. Guidelines for making the structures are to put the atom with the fewest valence electrons, except for hydrogen, in the middle of your structure. All of your nonmetals are trying to get to 8 valence electrons, except for hydrogen, which gets 2. And that's because for nonmetals, the noble gas state has 8 valence electrons, except hydrogen is trying to reach a noble gas state corresponding to helium, which only has 2 valence electrons. Bonds are formed between two shared electrons, so every bond should count as 2 valence electrons. Your total electrons used in the structure must equal the total valence electrons of all the atoms involved. So let's look at some examples. In this example, I have methylene chloride, which is the name of this chemical here, which has 1 carbon, 3 hydrogens, and 1 chlorine. The first thing I like to do is total up my valence electrons, so I know what my number of valence electrons in my final structure should be. So I have 1 carbon times, and I want to use my quick rule here for finding valence electrons, 1, 2, 3, 4 for carbon. So 1 carbon times 4. I have 3 hydrogens times 1. And I have 1 Cl times 1, 2, 3, 4, 5, 6, 7. So my total valence electrons in the structure should be 14. At this point, I want to say this guy is going to go in the center because it has the fewest valence electrons except for hydrogen. So I'm going to make a carbon, and I want to give it its 4 valence electrons. And I'm going to put everything else around it. I have 3 hydrogens, each with 1. And I have 1 chlorine, which has 7. So if carbon is trying to get to 8 valence electrons, it has 4. That means it needs to make 4 bonds. Each hydrogen is trying to get to 2, and it currently has 1, so it needs to make 1 bond. And the chlorine is trying to get to 8, and it has 7, so it needs to make 1 bond also. So what we can see here is the carbon is going to go in the middle because it needs to make the most number of bonds. It needs to make 4. And I have 4 other atoms around it that each need to make 1 bond. So we're going to be able to work this out pretty simply. All of these pairs of electrons can get shared to form a bond. So I'm going to redraw that with lines representing the bonds. Okay. It's very important to leave any pairs of electrons that weren't involved in bonding shown on the structure. So all of these pairs have now gotten turned into lines to represent bonds. These 6 electrons on chlorine aren't involved in any bonding, so they just need to show up on your final structure just as dots. So let's check to see how this solves everything. My nonmetals that aren't hydrogen need to have 8. Each bond counts as 2, so this carbon has 2, 4, 6, 8. And this chlorine has 2, 4, 6, 8. And all of my hydrogens need to have 2. So 2, 2, 2. So all of my atoms have the right number of valence electrons. And my total was supposed to be 14. So let's check and make sure I've matched that total. 2, 4, 6, 8, 10, 12, 14. So I satisfied the 2 criteria that I needed to meet. All my nonmetals have reached their noble gas state, and I've done it without exceeding my allowed number of electrons. Let's do another example. Okay, I have PF3, so I'm going to make my total. I have 1 phosphorus times 1, 2, 3, 4, 5. And I have 3 fluorines times 1, 2, 3, 4, 5, 6, 7. So my allowed total is 26. My rule tells me to put phosphorus in the middle because it has the fewer valence electrons. So I'm going to put a phosphorus in the middle, and I'm going to give it 5 valence electrons. And I'm going to put the fluorine atoms around it, and they get 7. You may notice that I'm pairing up the side with only 1 dots on these atoms because I know that that's where I'm going to be forming my bonds. It just helps me organizationally so that I have all of my dots that maybe aren't going to get involved on the bonds out on the outside. So looking at this, phosphorus has 5, it's trying to get to 8, so it needs to make 3 bonds. And each of my fluorines have 7, and they need to make 1 bond to get to 8. So I have the central atom that needs to make 3 bonds, and I have 3 atoms around it that each need to make a bond. So I'm going to be joining these pairs of electrons up to form bonds. So let's redraw that as my final structure. Phosphorus in the middle, bonded to fluorine, bonded to fluorine, bonded to fluorine. And again, it's very important to show any of the electrons that aren't involved in any bonding back on the original or on your final structure. Okay, so let's check. Phosphorus has 2, 4, 6, 8, so that's fine. Each fluorine has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And my total was allowed to be 26. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I met both my criteria. Okay, in this example we're going to see something slightly different happen. This is a molecule known as formaldehyde. It's what they use to pickle you. So it has 1 carbon times 1, 2, 3, 4. 2 hydrogens times 1. And 1 oxygen times 1, 2, 3, 4, 5, 6. So my allowed total on this structure is 12. My carbon is going to go in the middle because it has the fewest valence electrons, except for hydrogen. Dot, 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 4 dots. And again, I'm going to line up my atoms with the 1 dot next to it so that I know that those are going to end up forming bonds. Now I look at this one, I see my carbon needs to make 4 bonds because it only has 4 electrons, needs to get to 8. But I only have 3 atoms, which tells me one of these atoms is going to have to serve double duty. It can't be the hydrogens because they only want 2 valence electrons, so they're only ever going to make one bond. However, my oxygen has 6. It needs to make 2 bonds. So instead of making a single bond in this case, I'm actually going to end up making a double bond. First, I'm going to go ahead and make these bonds between the carbon and the hydrogen. My carbon now has 2 valence electrons left that it needs to form bonds with, and my oxygen has 2 valence electrons that it needs to form with too. So instead of forming just one bond, this is going to form a double bond. And let's clean this up some. So carbon in the center, bonded to a hydrogen, bonded to a hydrogen, and now I have a double bond to this oxygen. And let's check my totals. My hydrogens have 2. 1, 2, 2. My carbon has 2, 4, 6, 8, because now instead of just sharing 2 with the oxygen, it's sharing 4. So 2, 4, 6, 8. And the same thing goes for my oxygen. 2, 4, 6, 8. And my total has been done without exceeding 12. 2, 4, 6, 8, 10, 12. A common mistake that a lot of students like to do is they get in the habit of having pairs of dots on every side. So they might go ahead and add dots here and dots here. But that's not correct, because if we had extra dots on either the carbon or the oxygen, they would get to count for 10 valence electrons. 2, 4, 6, 8, 10, which is more than they're trying to get to because they're trying to reach 8. So be careful for that. Let's do a couple more with some extra bonds in it so you can see some more practice with those. Again, carbon, 4 electrons, 2 oxygens, 6 electrons. So my total is 16. Carbon goes in the middle because it has the fewest valence electrons. Dot, 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 dot. Oxygen goes on the outside. And we've got a similar predicament here. I have a carbon that needs to make 4 bonds, but I only have 2 atoms. So that means in this case, both of these atoms are going to be doing double duty. And that works out just fine because each oxygen has 6, and that means they need to make 2 bonds as well. So we're going to have double bonds between both of these atoms. Bond, double bond, bond, double bond. And let's clean this up. Carbon, double bond to oxygen, double bond to oxygen. I want to be really careful again about how many extra dots I'm shown that aren't involved in any bonding. 4 dots on this oxygen, 4 dots on this oxygen. I want to check to make sure everything works out. My carbon has 2, 4, 6, 8. Each oxygen has 2, 4, 6, 8, 2, 4, 6, 8. And my total should be 16. 2, 4, 6, 8, 10, 12, 14, 16. So everything's worked out. Let's do one more example. This is hydrogen cyanide. Definitely some dangerous stuff. So let's work this out. I have 1 hydrogen times 1. I have 1 carbon times 4. And I have 1 nitrogen times 1, 2, 3, 4, 5. So in this structure, I should use 10 valence electrons. Again, carbon is going to go in the middle because it has the fewest valence electrons, except for hydrogen. So carbon in the middle with 4 valence electrons. The other 2 atoms on either side. Okay. In this situation, I see that again, my carbon needs to make 4 bonds, but only 2 atoms. However, unlike in CO2, I can't make a double bond between carbon and hydrogen because hydrogen only wants to make one bond to get to count its 2 valence electrons, and that's it. So carbon now needs to make, instead of a double bond, a triple bond between carbon and nitrogen, which works out just fine because this nitrogen has 5, so it needs to make 3 bonds also. So single bond, double bond, triple bond. And let's clean this structure up. Hydrogen, single bond, triple bond, and key thing, only one pair of electrons that aren't involved in any bonding. Let's count. 2 for the hydrogen, that's cool. 2, 4, 6, 8 for carbon, that's cool. 2, 4, 6, 8 for nitrogen, that's good. And my total is 2, 4, 6, 8, 10, which matches, so everything's there. I hope this video helps you solve any of the problems that have either single, double, or triple bonds on covalent bonding, and we'll talk to you later.